Next, let's do an example of integration using cylindrical coordinates. So I have just a normal function x squared plus y squared here, but in this case, we're integrating over this region W that's given by the cone below. And I gave the equation of the cone z equals the square root of x squared plus y squared, meaning that the ratio of the z's to the x squareds plus y squareds is 1 in this case. Now I'm going to convert this into cylindrical coordinates in part because an equation for this cone is easy in cylindrical coordinates. Let's do a little bit of algebra to be able to solve this. You can also visualize what's going on as well. Recall that in polar coordinates, we have that r is equal to the square root of x squared plus y squared using Pythagorean theorem down in the xy plane. That means that in cylindrical coordinates, setting z equal to the square root of x squared plus y squared is going to be the same thing as having z equals r in cylindrical. And that's the equation of this cone where the slope of the sides of the cone is 1, meaning the ratio between the radius, as you go out 1 unit in radius, you're going to go up 1 unit in height. Let's look at the bounds of this region. First, we have to think about what happens if we project this down into the xy plane. What are the polar bounds of the base of this region? So I'm going to say the base is the shadow in the xy plane. And in this case, we're going to describe that base in polar coordinates. So notice in polar coordinates, we want to include the entire cone. So theta is going to go in a full circle, meaning that 0 is less than or equal to theta is less than or equal to pi over, or 2 pi, excuse me. And the radius in this case, we want to include the shadow underneath the entire cone, which would include my radius starting at 0 and going all the way out until a radius of 2. And I know that my radius is 2 because this figure has been labeled to have a height of 2. And if z equals r, then my maximum radius value is going to be 2. So r is from 0 to 2. Finally, what are the bounds on my z values in this case? But the z values, if you're thinking of sort of the height in this cone, they start down here at the line z equals r, and they extend upward until z hits a maximum value of 2. That means that the bottom bound on my z value is r, whereas the top bound on my z value is up at 2. So this is my bottom bound on z, and 2 is the top bound on z. So what does that leave us with? We've set up our bounds. We need to convert our x squared plus y squared into cylindrical coordinates, and then add our factor of integration, and then we will be ready to integrate. So we're letting our theta go from 0 to 2 pi. We're letting our r go from 0 to 2. Our z value, z, is equal to r on the bottom and 2 on top. Notice that I need to make sure that I have this z function inside of the r function. I could mix up the outer two, but because this is a function of r, it needs to be on the inside of the function. I need to convert x squared plus y squared, whoops, because that's what this function looks like, x squared plus y squared. And I have a hint. To convert that to polar coordinates, I know that x squared plus y squared is r squared. I could also go through the process of simplifying the fact that x equals r cosine theta, y equals r sine theta, and squaring each of those, I can simplify this to be r squared times cosine squared theta plus sine squared theta equals cosine squared plus sine squared equals 1 as a trig identity, and that means that this equals r squared. So either way, Then, because I'm integrating in cylindrical coordinates, I need to remember that I multiply by my factor, my red factor r, and my bounds of integration, my differentials are dz, dr, d theta. So I've set up my integration, and now comes the boring part of integrating. If you're bored with integrating, then you don't have to watch the rest of this. If you'd like the review, you can continue watching. It ends up being a pretty straightforward integral. So we can simplify this to r cubed. I have my triple integral. Theta goes from 0 to 2 pi. R goes from 0 to 2. Z goes from r to 2 of r cubed. dz, dr, d theta. My first step, I'm going to integrate with respect to z. That means I'm treating r cubed as a constant. So when I integrate a constant with respect to z, I'm going to multiply it by z. This is something that people sometimes forget. Whoops, it's not a triple integral anymore. Because I've integrated with respect to z, I'm going to evaluate my z as it goes from r to 2, but I still have two outer integrals. Why is this the case? Well, integration is the same as anti-differentiation. If I think of taking the derivative of this, where r is a constant and z is the variable, clearly the derivative would yield r cubed, because r cubed is the constant. So let's evaluate this. As I evaluate it as z goes from r to 2, that means my upper value is going to be 2r cubed, and then I'm going to subtract the lower value where z is equal to r, gives me r to the fourth. Oops. And I still need to integrate this twice with respect to r and theta. I'm going to move my work over here. My next integration is as r goes from 0 to 2. So let's integrate with respect to r. That becomes r to the fourth and 2 divided by 4. Maybe I'll write that out really clearly. 2 divided by 4, r to the fourth, minus 1/5 r to the fifth, evaluated from 0 to 2, d theta. We still have that outermost integral. Let's evaluate these bounds. 2 to the fourth is 4 times 4, which is 16, and 1/2 of 16 is 8. 2 to the fifth is 32 over 5. And finally, I'm going to do my final integration of this with respect to theta, as theta goes from 0 to 2 pi. I was being lazy and not writing my bounds every single time, but that's okay. You guys can follow along. Again, this is a constant that I'm going to integrate with respect to theta. So I'm going to be lazy again and not simplify 32 fifths and 8. So when I integrate or take the antiderivative, I'm treating this as a constant, and I'm going to evaluate theta as it goes from 0 to 2 pi. So it means that my final answer, it's going to be a little cramped in here, but it's going to be 2 pi times 8 minus 32 fifths. If I wanted to, I could get a common denominator here by multiplying 8 times 5, which is 40, and then subtracting 32. 40 minus 32 is 8. So I'm left with 8 fifths. So this simplifies, I believe, to being 16 pi over 5. But you should check my arithmetic.